So let's go to example 14. We need to determine the specific volume of a superheated water vapor at a 3.5 megapascal and 450 degrees C based on three things. The first one is the ideal gas equation. The second one is the generalized compressibility chart as well as the steam table. And we need to determine the error involved in the first two cases. Okay? So here I just talk about the solution because I need to tell you how to use this generalized compressibility chart because it's a little bit tricky here. So first of all, let us do the very easy part. Part A, we approximate it by using the ideal gas equation. Okay, so that means we just use PV equal to RT. Because we need to find the specific volume, so we use small letter v. And we just plug in the values. Okay, pretty easy indeed. So what's the P? The P is 3.5 megapascal, so we have 3500 here. Remember, we need to change it to kilopascal, where we need to use this ideal gas equation. And V is what we need to find. How about R? Okay. We can guess this from table A1. For water, we have the R to be 0.4615. 0.4615. And because we only have one value, so we just take this value. So 0.4615. How about the temperature? Okay, the temperature is 450 degrees C. So 450 plus 273. Okay. So the V just equal to 0.09533. Okay. So this is part A. Okay. We will later determine the error. Okay, for part B, because we know the pressure and the temperature, so we will just use the generalized compressibility chart easily. So first of all, if we need to use that chart, we need to calculate the reduced pressure first. The reduced pressure is P divided by P critical. What's that? Here, if you check table A1, you will see that this is the critical temperature, 647.1. And this one is the critical pressure. But note that this is in megapascal. And this one is K. So we'll have 3.5 megapascal divided by 22.06 megapascal. Okay, and you will get 0.1587. Okay, how about the reduced temperature? The reduced temperature is similar. So note that 450 plus 273 is 723. So we have 723 divided by 647.1 equal to 1.117. Okay, and we need to use these two values to find out the compressibility factor. How can we find that? Let's go to the compressibility table. Okay, let's see. We have a reduced pressure to be 0.1587. Okay, so we will go to the A graph. Okay, the A graph. The reduced pressure is here, 0.1587. So I approximate it to be 0.16. So somewhere here. And for the reduced temperature is 1.117. So here you can see that this TR is a 1 and 1.05, 1.10. And because our value is 1.117, so we have a curve that lies between this. Okay, and you just check 0.16 as well as this intermediate curve, the imaginary curve. And you will see that it's about 0.961. You may get just only 0.96. That's fine, as long as you do not pose a number with a very much error. For example, Z equal to 0.5, and that's okay. Okay, so we can get the actual volume by this one. Because we have got the ideal gas volume, if we assume that this water is ideal gas, so we just find out the actual one by ZV ideal, which is 0.961 multiplied by 0.09533, which is equal to 0.09161 meter cube per kg. Okay. Okay, finally, we can get the actual data from the steam table. So we have the pressure equal to 3.5 megapascal and the T equal to 450 degrees C. And we can get the actual value from the steam table. That means the table A6. So from table A6, you will find that, so 3.5 megapascal and the temperature is 450, so we get this one, 0.09198 meter cube per kg. Okay, so this is the actual value. And we need to also determine the error involved in the first two cases. How can you get the error? Easy, you just find out the change, and then you just divide it by this number multiplied by 100% to get the error. And we will see that in this case, we have 0.4% error. For this case, actually it differs much, about 3.64% error. Okay, so much greater error indeed. So we can see that the compressibility factor has helped us to reduce the error. Okay, however, the procedure of obtaining this compressibility is actually quite tedious. Okay, as you can see from that horrible chart. Okay, in my opinion, it will be only about 10% of chance that you will see it in exam, but you may see this in your homework. Okay, so I need to also introduce this compressibility chart to you. Okay, so that's example 14.